Hello, friend. Welcome to Science for Sleep. Did you know that raindrops are not actually shaped like tears? Most drawings show them as little pointed droplets, wide at the bottom and narrow at the top, as if each drop was stretching itself into a tiny falling flame. But in reality, when rain forms in the sky, the smallest drops are nearly perfect spheres, held together by surface tension, rounded and smooth. Larger drops flatten slightly as they fall, pressed gently by the air beneath them, becoming more like soft, curved buns than teardrops. Even something as ordinary as rain holds quiet corrections to what we think we know. Rain begins long before it touches the ground. It begins as invisible water vapor rising from oceans, lakes, soil, and even the quiet moisture leaving leaves. Warm air can hold more water than cool air, and as that air rises and cools, the vapor condenses into tiny droplets too small to see. Billions of those droplets gather into clouds, suspended high above, waiting for gravity to do its patient work. And when those droplets finally grow heavy enough to fall, something else happens that is easy to overlook. The water landing on your hand during a storm has been here before. The very same water. The atoms inside that drop are ancient. Water on Earth moves in a cycle. It rises, cools, gathers, falls, flows, and rises again. It does not vanish. It changes place. Imagine rain falling onto the metal armor of a knight, standing on a quiet battlefield, long before electric lights, the sky heavy and grey above him. The water that touched his shoulder may be part of the same water that touches your window tonight. Imagine rain sliding down the stone face of a pharaoh in ancient Egypt, tapping softly against limestone carved thousands of years ago. That same water, moving through centuries, may now rest briefly in the cloud above your city. Imagine that water soaking into the thick hide of a dinosaur beneath a warm prehistoric sky. The forests were different then. The air was thicker. The shapes of life were larger. But the water was the same. Water has been here for billions of years, cycling through eras without hurry. It is possible that the rain you have seen in your lifetime once moved through a glacier, or drifted through the open Atlantic Ocean, or rose invisibly from a sunlit lake at dawn. The water cycle is continuous. Evaporation lifts it. Cooling gathers it. Gravity returns it. Nothing about the process is happening at a fast pace. If you enjoy these quiet journeys, you're welcome to subscribe. And if it feels natural, to leave a comment sharing where you're listening from tonight. It helps others find their way to this calm corner of the world, one sleepy traveler at a time. Rain may or may not be falling where you are right now. Perhaps the air outside is still. Perhaps there is a faint tapping on glass. Or perhaps the sky is clear, and the process is unfolding somewhere far away, over an ocean or mountain range. Whether present or absent, rain is always part of the planet's slow circulation. Somewhere above, air is cooling. Somewhere else, droplets are merging. Somewhere else, gravity is beginning its gentle pull. The next time rain touches your skin, you can remember that it is both newly formed and unimaginably old. Rounded, not tear-shaped. Familiar, yet quietly complex. A small falling sphere carrying the memory of oceans, rivers, ancient nights, and distant ages. Tonight, we will move slowly through this process together, from invisible vapor to falling drop, from scent to sound, from cloud to soil and back again. The air changes before the rain begins. Long before a drop touches the ground, something subtle moves through the space around you. The light may soften, the wind may quiet, and sometimes, before the first sound of rain reaches your ears, there is a scent. That scent has a name. It is called petrichor. Petrichor is the earthy smell that rises from dry ground just before rainfall. It is not imagination. It is not memory playing tricks. It is chemistry meeting the air. During long dry periods, plants release small amounts of natural oils into the soil. These oils settle into rocks and dust, lingering there quietly. At the same time, tiny organisms in the soil, especially a group of bacteria called actinobacteria, produce a compound known as geosmin. Geosmin is what gives soil its deep, earthy scent. It is present in very small amounts, but it waits there patiently in the ground. When rain begins to fall, the impact of the drops disturbs the surface of the soil. The drops trap tiny air bubbles as they hit. Those bubbles rise back up through the thin film of water and burst, releasing microscopic particles into the air. Among those particles are plant oils and geosmin. The scent rises before the rain fully settles. Humans are remarkably sensitive to geosmin. We can detect it in extremely low concentrations, even when only a few molecules are present in the air. In fact, our ability to smell geosmin is stronger than many other animals. The nose recognizes it quickly, almost instinctively. So if you have ever paused and said, "It smells like rain," you were correct. Your body noticed. There is another layer to this process. When lightning occurs during a storm, the electrical energy can split oxygen molecules in the atmosphere. Some of those oxygen atoms recombine into ozone, which has a sharp, clean scent. Winds ahead of a storm can carry that ozone downward. Sometimes what you are smelling before rainfall is a faint trace of that electrical change in the air. Rain announces itself quietly through chemistry. And there is something deeply grounding about that. The smell before rain is not only about memory or comfort. It is about detection. For much of human history, being able to sense rain would have mattered. Rain meant water for crops. It meant rivers refilling. It meant relief from heat. The ability to detect a shift in the air could signal change before it arrived. Even today, when most people no longer depend directly on rainfall for survival, the body still responds. As clouds gather overhead, warm air rises and cools. Cooling air cannot hold as much water vapor as warm air can. When air reaches its dew point, the temperature at which moisture condenses, water begins to gather onto tiny particles floating in the atmosphere, such as dust or salt. Those microscopic droplets are the beginning of a cloud. While that is happening high above, the ground below is waiting. The scent rises upward just as the droplets prepare to fall downward. There is something balanced in that exchange. The earth releases its stored oils into the air, and the sky releases its stored water toward the earth. The cycle moves in both directions. You may remember standing outside as a child, noticing the smell before a storm, the air feeling heavier, quieter. Perhaps you watched leaves turn slightly upward as wind shifted direction. Perhaps you felt a faint coolness move across your skin. Those sensations are not random. Humidity increases as more water vapor fills the air. Higher humidity slows evaporation from your skin, making the air feel thicker. Pressure can drop slightly before a storm, contributing to that subtle sense that something is changing. The atmosphere is never still. It is always holding, releasing, adjusting. Right now, somewhere above the planet, air is rising and cooling. Somewhere, soil is releasing its stored scent. Somewhere, droplets are gathering onto particles too small to see. The smell before rain is the first whisper of gravity, preparing to act. In the next quiet movement of this process, the droplets themselves will begin to take shape, rounding into forms that are almost perfectly smooth, shaped by forces you cannot see, but that have always been present. The air shifts, the scent rises, the sky gathers, and slowly the descent begins. High above the ground, before any sound of impact or shimmer on pavement, a single droplet begins to take form. It does not begin as a falling tear. Inside a cloud, water gathers in tiny spheres, each one so small it could rest on the tip of a hair. These droplets form when water vapor cools and condenses onto microscopic particles floating in the air. Dust, sea salt, even faint traces of smoke can act as a surface for condensation. Around each particle, moisture collects, building layer upon layer, until a visible droplet exists where once there was only invisible vapor. At this early stage, surface tension shapes the droplet. Surface tension is the force that pulls the molecules of water together, allowing them to cling to one another. It is the same force that lets water bead on a leaf or form a rounded drop on glass. Because water molecules attract each other strongly, they naturally form into shapes that minimize surface area. That shape is a sphere. So inside the cloud, the smallest raindrops are nearly perfectly round. They are not stretched. They are not pointed. They are small floating spheres, suspended by rising air currents that gently push upward. A cloud can contain billions of these droplets, each one drifting slowly, supported by subtle upward motion in the atmosphere. But clouds are not still places. Within them, droplets move. They collide. They merge. When two droplets bump into each other, they can join together in a process called coalescence. The new droplet becomes larger and heavier. As it grows, gravity begins to matter more. There comes a moment when the droplet is too heavy for the rising air to hold. That is when it begins to fall. As it falls, air pushes back against it. This upward force, called air resistance, reshapes the droplet. For very small drops, the air pressure is not strong enough to change the shape much. They remain nearly spherical as they descend. But larger droplets feel more resistance beneath them. The bottom of the drop flattens slightly, pressed upward by the air it moves through. The top remains curved. The result is not a tear, but a shape more like a small, rounded bun, wider at the base, smooth at the top. If a drop grows too large, something else happens. Air resistance can stretch it so much that it becomes unstable. The flattened bottom can curve upward, and the droplet may break apart into smaller drops mid-air. There is a natural limit to how large a raindrop can become before it fragments. Most raindrops fall at speeds between about 14 and 22 miles per hour, depending on their size. This speed is known as terminal velocity. Terminal velocity is reached when the downward pull of gravity equals the upward push of air resistance. At that point, the drop stops accelerating and falls at a steady speed. Each falling drop is shaped by a balance of forces. Gravity pulls downward, air pushes upward, surface tension holds the water together. All of this happens silently, thousands of feet above the ground, before a single drop reaches a rooftop or leaf. And while this shaping is taking place, something else is also true. Many of these droplets began as ice, in tall clouds that stretch high into the atmosphere. Temperatures can be far below freezing. Ice crystals form first, even during warm weather. Those crystals collide with supercooled water droplets and grow larger. As they descend into warmer air layers, they melt into liquid drops. By the time they reach your hand, they feel soft and warm, but moments earlier they may have been frozen. The shape of a raindrop is a story of balance. It begins round in stillness, flattens slightly in motion, and sometimes breaks apart if pushed too far. It is never sharp at the top, never stretched into a point. The familiar image in drawings does not match the quiet physics unfolding in the sky. And as millions of these rounded drops fall together, they create patterns of sound and motion that feel steady and calming below. The next movement in this process is not about shape, but about variety. Not all rain falls the same way. Some forms drift softly, others fall in sheets. Some begin in rising heat, others form where air masses meet. The rounded drop is only the beginning. The sky holds many ways of letting water descend. Not all rain arrives in the same way. The rounded drops that fall from the sky may look similar once they reach the ground, but the paths that bring them there can be very different. The atmosphere has several quiet methods for lifting water upward and returning it again, each shaped by temperature, pressure, and movement in the air. Sometimes rain begins with warmth rising. When the sun heats the surface of the earth, the air just above the ground warms as well. Warm air is lighter than cool air, so it rises. As it rises, it expands and cools. Cooling air cannot hold as much water vapor, and once it reaches its dew point, condensation begins. Droplets form. Clouds build upward. This is called convective rain. Convective rain often appears in the afternoon, especially in warmer climates. You may have noticed how a clear morning can slowly give way to tall, growing clouds by late day. Those clouds can stretch high into the sky, sometimes reaching heights of 30,000 or even 40,000 feet. Within them, droplets collide, merge, and begin their descent. Convective rain can be brief but intense, falling in concentrated bursts before easing again. Other times, rain forms where two large air masses meet. A warm air mass and a cooler air mass move across the planet constantly. When they meet, the warmer air is forced upward over the cooler air. As it rises, it cools and condenses, forming clouds along a boundary known as a front. This process is called frontal rainfall. Frontal rain tends to cover larger areas and can last longer. Instead of sudden downpours, it often arrives steadily, tapping against rooftops and soaking into soil over hours or even days. The rising is more gradual, the condensation more widespread. The atmosphere lifts water not in a column, but along a long, invisible slope in the sky. There is also rain shaped by the land itself. When moist air moves toward a mountain range, it cannot pass straight through. It is forced upward along the slope. As the air rises, it cools. Cooling leads to condensation. Clouds gather along the peaks, and rain falls on the side facing the incoming wind. This is known as orographic rainfall. On the other side of the mountain, the air descends and warms again, often creating dry regions called rain shadows. In this way, mountains quietly shape where rain falls and where it does not. And sometimes, what reaches the ground is softer still. Drizzle consists of very small droplets, often less than 0.5 millimeter wide. These droplets fall slowly, sometimes drifting almost sideways in light wind. Because they are so small, they produce a gentle sound, almost like a whisper against leaves. Steady rain contains larger droplets. They fall faster, strike harder, and create the rhythmic patterns many people recognize instantly. The size of the drop changes the sound. The speed changes the feel. There is also rain that begins as snow high above and melts as it passes through warmer layers of air. If the air near the surface is cold enough, droplets can freeze again upon contact, creating freezing rain. Each form depends on temperature layers stacked invisibly in the atmosphere. The variety of rain is shaped by motion. Air rises because it is warm. Air rises because it meets another air mass. Air rises because it meets a mountain. In each case, the rising is what matters. Cooling follows. Condensation begins. Droplets grow. And eventually, gravity takes over. The sky does not release rain randomly. It follows quiet physical rules that have always been present. Warm air holds more moisture than cold air. Rising air cools. Cooling air condenses. Heavier droplets fall. Below, on the ground, the experience may feel simple. You step outside. The air is damp. The sky is grey. Drops land softly on your sleeve. Above, the process is layered and vast. As these different forms of rain fall, they begin to create something else. They create sound. They create cooling. They alter the way the air feels against your skin. In the next quiet shift, attention moves from how rain forms to how it meets the body, and how the steady pattern of falling water can gently change the state of the nervous system itself. When rain begins to fall steadily, something shifts not only in the sky, but within the body. The sound arrives first. A single drop striking a surface creates a brief vibration. That vibration moves through air as a wave. When thousands of drops fall together, the individual impacts overlap. Instead of sharp, separate noises, the sound blends into a continuous pattern. This pattern is often described as white noise, a broad mix of frequencies that fills the background without sharp edges. White noise works by masking sudden changes. In a quiet room, a single unexpected sound stands out. A door closing in the distance, a passing car, a small creak in the floor. The nervous system is designed to notice contrast. Sudden changes signal potential threat. When the environment contains many unpredictable spikes, the body remains slightly alert. Rain reduces contrast. Because raindrops fall at slightly different speeds and strike at slightly different times, the resulting sound is complex but steady. The constant layering of impacts smooths out sharp variations. sudden noises become less distinct against the background wash. The nervous system registers fewer abrupt changes. This allows vigilance to soften. There is a branch of the nervous system called the parasympathetic system. It supports rest, digestion, and recovery. When stimulation decreases and the environment feels predictable, parasympathetic activity increases. Heart rate can slow slightly. Muscles may relax. Breathing often deepens without effort. Rain creates predictability. Even though each drop falls independently, the overall pattern remains steady. The sound does not demand attention. It does not change suddenly. It continues at a consistent pace. This consistency allows the mind to drift without needing to track each separate event. The rhythm matters. Studies of auditory perception show that low-frequency, consistent sounds are less likely to trigger stress responses than sharp, high-frequency bursts. Rain contains a wide range of frequencies, but the dominant tones are soft and layered. When rain falls on leaves, the sound is diffused. When it strikes soil, it is absorbed. When it taps against a window, it spreads across the glass before fading. Each surface shapes the tone, but the overall effect remains continuous. There is also a visual component. Rain reduces visual sharpness. As droplets fall through the air, they scatter light. The sky becomes more uniform. Edges soften. Distant objects appear slightly blurred. Reduced visual contrast means the eyes process fewer distinct details. With fewer sharp visual cues, the brain has less information to monitor. Less monitoring means less alertness. Humidity plays a role as well. As rain approaches, moisture in the air increases. Higher humidity slows the evaporation of sweat from the skin, creating a subtle sensation of warmth or heaviness. This physical shift can encourage stillness. When the air feels thick and steady, movement often slows naturally. Temperature changes also contribute. Rain-cooled air descends from higher altitudes, lowering surface temperatures slightly. Cooler air can reduce restlessness, particularly after warm days. The body responds to temperature shifts without conscious thought. Rain alters sound, light, temperature, and touch all at once. It lowers environmental intensity. For much of human history, steady rain often meant sheltering in place. Outdoor tasks paused. Fires burned indoors. Movement slowed. Over time, these repeated experiences may have reinforced the association between rainfall and reduced activity. The body learns patterns through repetition. Even now, when daily routines are less dependent on weather, the association remains. You may have noticed how the first steady rainfall at night feels different from silence. Silence can feel sharp. Rain feels full. It fills empty space with gentle sound. Instead of listening for what might happen next, the ear settles into what is already happening. The rain does not ask anything from you. It continues whether you focus on it or not. And as droplets fall, round and balanced, shaped by air and gravity, the background sound they create becomes something steady enough to rest within. In the quiet continuation of this process, attention begins to drift toward the way those droplets meet different surfaces, how each leaf, rooftop, and patch of soil shapes the tone slightly differently. The sky releases water. The ground answers with sound. And the body, sensing predictability, begins to soften along with it. Rain continues to fall, steady and rounded, shaped by gravity and air. Now the ear begins to notice something else. The sound of rain is never only one sound. When a drop strikes a broad green leaf, the impact spreads across a flexible surface. The leaf bends slightly, absorbing part of the energy. The vibration softens quickly. The resulting sound is light, almost hollow, a soft patter that seems to disappear as soon as it arrives. If many leaves overlap, each one adds a faint variation in tone. Together, they create a layered whisper. When rain meets soil, the effect is different. Dry soil absorbs water quickly. The drop sinks in, breaking apart as it enters tiny spaces between grains of sand and clay. The sound is muted. Soft ground reduces vibration. Instead of a sharp tap, there is a gentle thud that fades almost immediately. If the ground is already wet, the drop may strike a thin film of water, creating a faint splash before being absorbed. Hard surfaces respond differently. When rain hits a metal roof, a window, or a paved road, the drop cannot sink in. The energy has nowhere to go but outward. The surface vibrates. That vibration travels through the material and into the air as a sharper sound. Hard surfaces amplify. They reflect the impact rather than absorb it. This is why rain on a tin roof sounds louder than rain in a forest. Each material shapes the sound by either absorbing energy or reflecting it. Even water itself changes the tone. When rain falls into a pond or lake, each drop creates a small circular ripple. The drop briefly pushes into the surface, forming a tiny crown-shaped splash before settling. The sound is lighter and more dispersed than on stone. Because water yields easily, much of the energy is transferred into motion rather than sound. Ripples spread outward in quiet rings. Drop size also matters. Smaller droplets, like those in drizzle, produce higher frequency sounds. They strike gently, creating lighter taps. Larger drops contain more mass and fall faster. When they hit a surface, they release more energy, producing lower, fuller tones. A heavy rainstorm sounds deeper than a misty shower. As millions of drops fall, these differences blend together. Some strike leaves, some strike glass, some land in puddles. The ear does not isolate each sound separately. Instead, it hears a composite pattern. The repetition creates a rhythm without a beat. There is no melody. There is no sudden crescendo. Just continuous variation within a stable background. This stability is important. The auditory system responds strongly to unpredictability. Sudden, irregular spikes draw attention. Rain, even when heavy, tends to remain statistically consistent. The spacing between drops varies, but within a narrow range. The average intensity remains similar from one moment to the next. The result is a steady acoustic field. You might notice how rain sounds fuller when it first begins, as isolated drops strike dry surfaces. Each drop stands out clearly. Then, as surfaces become wet, the sound changes. Water cushions further impacts. The tone becomes softer, more blended. The environment shifts from sharp to smooth. Inside a room, the structure of the building shapes the experience again. Rain on a roof travels through beams and panels before reaching the ear. Walls filter higher frequencies. Glass reflects sharper tones. Curtains and fabric absorb vibration. Each home becomes its own instrument, translating falling water into a unique pattern of sound. Outside, trees act as diffusers. Leaves scatter droplets in multiple directions. Branches redirect falling water. The canopy breaks large drops into smaller ones. Beneath a forest, rainfall may sound more like a scattered hush than a direct tapping. The environment collaborates with the rain. Every surface participates. As the sound continues, something else is happening quietly in the air itself. The falling water interacts with temperature. The evaporation of droplets can cool the surrounding air slightly. Downdrafts begin to form high above, carrying cooler air downward. The sound remains steady, but the atmosphere is shifting. The next quiet movement of this process is not about impact, but about cooling. The air that carries these sounds begins to change temperature, and that change carries its own subtle effect. The sound continues, steady and layered, but the air itself is changing. Long before rain reaches the ground, subtle shifts in temperature begin to unfold above and around you. These shifts are not dramatic. They do not arrive all at once. They move gradually, carried by invisible exchanges of energy within the atmosphere. When water evaporates, it absorbs heat. This process is called evaporative cooling. As liquid water turns into vapor, it requires energy to break the bonds holding its molecules together. That energy is taken from the surrounding air. The air cools slightly as a result. On warm days, you may have felt this when stepping out of a pool. Water evaporating from your skin draws heat away, leaving you cooler. The same process happens on a much larger scale in the sky. As rain begins to fall through dry air, some of the droplets evaporate before reaching the ground. This evaporation cools the air through which the drops are falling. The cooled air becomes denser and heavier than the air around it. Because denser air sinks, it moves downward in a gentle current known as a downdraft. These downdrafts can carry cooler air from higher altitudes down toward the surface. That is why, just before or during rainfall, you may notice a soft drop in temperature. The change is not sudden, but perceptible. A warm afternoon can shift into something fresher, calmer, slightly cooler. There is another exchange taking place at the same time. While evaporation absorbs heat, condensation releases it. When water vapor in rising air cools and condenses into droplets, it releases energy known as latent heat. This release of heat warms the surrounding air slightly, helping clouds continue to grow upward. In tall storm clouds, this released heat can strengthen the upward motion, allowing the cloud to extend higher into the sky. So even within one storm system, cooling and warming occur together. High above, condensation releases heat. Lower down, evaporation absorbs it. The atmosphere balances these exchanges continuously. Closer to the ground, humidity increases as rain approaches. Humidity refers to the amount of water vapor present in the air. Warm air can hold more vapor than cool air. As a storm gathers, moisture accumulates, and relative humidity rises. When humidity is high, sweat evaporates more slowly from the skin. This can create a sensation of heaviness or thickness in the air. The body senses this. Skin receptors respond to changes in temperature and moisture. Even small shifts can alter how the air feels against your arms or face. As rain cools the surrounding environment, surfaces such as soil, pavement, and rooftops also cool slightly. This further changes the temperature of the air just above them. After rain passes, the air often feels clearer. Rain can remove small particles from the atmosphere. Dust, pollen, and pollutants are captured by falling droplets and carried downward. This process is sometimes called wet deposition. The result is air that feels lighter and easier to breathe. The scent of soil lingers, but sharp dryness fades. The freshness after rain is not imagined. It has physical causes. Cooler air holds less water vapor, which can make breathing feel smoother. Lower particulate levels mean fewer irritants suspended in the air. Even light levels shift as clouds thin and sunlight returns, reflecting differently off wet surfaces. The ground also participates in this exchange. When rain soaks into soil, it lowers surface temperatures. Wet ground absorbs heat differently than dry ground. Evaporation from damp soil continues the cooling process even after rainfall stops. This is why evenings after rain can feel calm and balanced, neither too warm nor too cold. All of these shifts happen gradually. There is no sudden switch. The atmosphere adjusts continuously, redistributing heat, moisture, and movement. The air that touches your skin is part of a larger system circulating around the planet. As rain falls, rounded and steady, it is not only delivering water, it is redistributing energy. And while the air near the ground cools, attention can lift gently upward again. Above, warm air continues to rise somewhere. Moisture gathers invisibly. Clouds hold vast numbers of droplets suspended in quiet balance. To understand how rain cools the air below, it helps to understand how those clouds hold water above. The sky is not empty. It is filled with suspended droplets so small they remain aloft, supported by rising currents. Billions of them gather together to form what we see as a single cloud. Cooling near the surface is only one part of the cycle. Higher still, water vapor continues to condense, waiting for the moment when suspension gives way to descent. The sound softens. The air cools. The sky holds. And above, in quiet suspension, the next stage of rain is forming. Above the cooling air near the ground, above the softened light and steady sound, the sky holds something that seems almost weightless. A cloud looks solid from a distance. It has edges. It casts shadows. It stretches across the horizon like a slow-moving landscape. But a cloud is not solid at all. It is made of countless tiny droplets of water, each one far smaller than the rounded drops that reach the ground. Warm air can hold more water vapor than cold air. This is a simple but powerful rule of the atmosphere. When air warms, the molecules inside it move faster and spread slightly farther apart, making room for more water vapor. When that same air rises, it expands as pressure decreases. Expanding air cools. As it cools, it loses some of its ability to hold vapor. When cooling reaches a certain point, called the dew point, water vapor begins to condense. But condensation does not happen in empty space. Water vapor needs a surface to gather upon. In the atmosphere, that surface is often a microscopic particle floating in the air. Tiny grains of dust, bits of sea salt carried inland from the ocean, fragments of pollen, even small traces of smoke can serve as condensation nuclei. Around these particles, water molecules cluster. A droplet forms. Each droplet inside a cloud is extremely small, often about 0.02 millimeters in diameter. That is much smaller than the raindrops that fall to the ground. A single visible cloud can contain billions upon billions of these droplets suspended together. And yet they do not immediately fall. They remain aloft because rising air supports them. Within a cloud, air is rarely still. Warm air continues to rise gently from below. These upward currents are called updrafts. As long as the upward motion of air matches or exceeds the downward pull of gravity on each tiny droplet, the droplets remain suspended. They drift, they swirl, they gather slowly. This balance between gravity pulling down and air lifting up creates the visible body of a cloud. From below, you may see a cloud as a flat layer stretching across the sky, or as a towering formation rising high above the horizon. The difference depends on how strong the upward motion is. Gentle lifting produces wide, layered clouds. Strong lifting produces tall, vertical clouds that can reach far into colder regions of the atmosphere. Inside these clouds, droplets move constantly. They collide softly with one another. They merge, they separate. The interior of a cloud is a place of continuous small motion, even though from the ground, it may appear calm and still. Temperature varies within a cloud as well. The lower parts may be above freezing, while the upper regions can be far below 0 degrees Celsius. In these colder layers, ice crystals may form alongside liquid droplets. Supercooled water, liquid water that remains unfrozen below its normal freezing point, can exist there as well. All of this is held in suspension. The whiteness of a cloud comes from the way these tiny droplets scatter sunlight. When light enters a cloud, it bounces in many directions off the surfaces of the droplets. Because the droplets are similar in size to the wavelengths of visible light, they scatter all colors roughly equally. The result is a soft white appearance. When clouds grow thicker, they appear darker from below, because less sunlight passes through. Yet even the darkest cloud is still made of droplets so small they float almost effortlessly. The cloud holds water that has risen invisibly from oceans, rivers, soil, and leaves. The vapor rose quietly, cooled, and gathered. Now it waits in suspension, supported by motion you cannot see. There is a stillness in this balance. Gravity pulls downward constantly. Updrafts push upward gently. As long as the forces remain nearly equal, the droplets remain suspended. The cloud drifts across the sky, carried by larger wind patterns moving at high altitudes. But suspension is temporary. As droplets collide and merge, they grow larger. As they grow, gravity gains influence. At a certain point, the upward motion is no longer strong enough to support them. The quiet suspension begins to shift toward descent. Within the body of the cloud, tiny collisions accumulate. Mass increases. Balance tips. The next movement in this process is gradual but inevitable. Droplets that once floated freely begin to gather weight. They merge, expand, and prepare for the moment when gravity overcomes the lifting air. Suspension gives way to falling. and the slow gathering inside the cloud becomes the beginning of rain once more. Inside the cloud, the balance begins to change. What once floated lightly in suspension now gathers weight, almost imperceptibly at first. Each tiny droplet, no wider than a strand of hair, drifts among billions of others. They move with the currents of rising air, colliding softly, separating, colliding again. Most collisions do nothing. Two droplets may touch and bounce apart. Surface tension holds each one intact. But sometimes, when conditions are just right, two droplets merge. Their surfaces join. Their combined mass becomes slightly larger than before. This process is called coalescence. It happens quietly and repeatedly inside a cloud. A droplet merges with another, then perhaps another. Each merger increases its size. With increased size comes increased mass, and with increased mass comes a stronger pull from gravity. At first, the upward currents of air still support the growing droplet. The cloud continues to hold it in suspension. But as merging continues, the droplet becomes heavier. Gravity's influence grows stronger than the lifting air. The balance tips. When gravity overcomes the upward push of the air, the droplet begins to fall. It does not accelerate forever. As it descends, air resistance pushes upward against it. Very small droplets fall slowly, drifting gently downward. Larger droplets fall faster. The greater the mass, the stronger the downward force. But the upward resistance also increases with speed. Eventually, the droplet reaches a steady falling speed, its terminal velocity, where gravity and air resistance are balanced once again. For most raindrops, this speed ranges between about 14 and 22 miles per hour, depending on size. But the story does not end with descent. As a droplet falls through the cloud, it may continue colliding with other droplets. It may grow larger still. Larger drops fall faster than smaller ones, which means they overtake droplets below them, increasing the chances of further merging. There is a limit to how large a raindrop can become. When a drop grows too large, air resistance flattens its underside dramatically. The drop becomes unstable. Instead of maintaining a smooth, rounded shape, it may begin to stretch and distort. At a certain point, the drop breaks apart into smaller droplets. This fragmentation limits the maximum size of natural raindrops. So within the falling rain, there is both growth and division. Some droplets merge, others break apart. The system regulates itself through physics alone. Inside colder clouds, another process can assist in making droplets heavy enough to fall. Ice crystals form in the upper regions where temperatures are below freezing. These crystals attract nearby supercooled water droplets, which freeze upon contact. The ice crystals grow larger and heavier. Eventually, they fall downward. If they pass through warmer layers of air, they melt into liquid drops before reaching the ground. This is known as the Bergeron process. In clouds containing both ice crystals and liquid droplets, ice tends to grow more quickly because water vapor deposits more readily onto ice than onto liquid water. This accelerates the formation of precipitation, especially in taller storm systems. Whether through coalescence among liquid droplets or growth of ice crystals in cold layers, the principle remains the same. Mass increases. Gravity strengthens. Suspension gives way to descent. From below, rain may appear uniform, but inside the cloud, It is dynamic and layered. Tiny particles of dust once acted as seeds. Vapor condensed around them. Droplets formed and drifted. Collisions occurred thousands of times per second across the cloud's interior. Eventually, some droplets crossed the invisible threshold where gravity's pull became dominant. That moment is quiet, but decisive. The droplet begins its journey downward, leaving behind the region of suspension. It falls through layers of air with different temperatures and densities. Wind may push it slightly sideways. Air resistance shapes it gently. Above, more droplets continue to merge. Below, the first drops approach the ground, and between sky and soil lies a long vertical distance, sometimes thousands of feet deep. Within that space, temperature changes, wind currents shift, and droplets adjust their form as they descend. To understand how rain feels at the surface, it helps to follow a single drop through that vertical path. From the moment gravity takes hold to the instant of impact, the fall itself becomes its own quiet chapter in the story of rain. High above the falling rain, in the tallest clouds, the air is far colder than it feels at the ground. Even on a warm afternoon, temperatures thousands of feet above the surface can be well below freezing. In large storm clouds, especially those that rise high into the atmosphere, the upper layers may reach temperatures of -20 degrees Celsius or colder. At these heights, water does not begin as liquid. It begins as ice. Inside these towering clouds, tiny ice crystals form when water vapor deposits directly onto microscopic particles. Instead of condensing into liquid first, the vapor freezes as it gathers. These crystals can grow into delicate six-sided shapes, similar to the structure of snowflakes. Around them, liquid droplets may still exist. In fact, water can remain in liquid form below its normal freezing point, in a state called supercooled water. These supercooled droplets are unstable. When they come into contact with an ice crystal, they freeze instantly, adding to the crystal's mass. This allows ice particles to grow rapidly in the cold upper regions of the cloud. As they grow heavier, gravity begins to pull them downward. They fall through layers of air that may be warmer than the region where they formed. If the temperature rises above freezing before the ice reaches the ground, the crystals melt into liquid droplets. By the time they touch your skin, they feel like ordinary rain. But moments earlier, they may have been frozen structures suspended in the upper sky. This layered structure of temperature is important. The atmosphere is not the same temperature from top to bottom. It changes gradually with height. These vertical temperature layers determine whether precipitation falls as snow, rain, sleet, or freezing rain. If the entire column of air from cloud to ground remains below freezing, the ice crystals do not melt. They reach the surface as snow. If there is a deep, warm layer below the cloud, the ice melts fully into liquid before reaching the ground. This becomes rain. If the ice melts into rain, but then passes through a shallow layer of cold air near the surface, it may partially refreeze into small ice pellets. This is sleet. And if the melted rain passes through very cold air just before reaching the ground, but does not have time to refreeze into pellets, it may remain liquid until it contacts a cold surface. Upon contact, it freezes instantly, forming a thin glaze of ice. This is freezing rain. Each form depends on the invisible temperature profile of the air above. From below, you may only feel liquid drops, but inside the cloud and along the path downward, a sequence of freezing and melting may have occurred. In very tall storm systems, such as cumulonimbus clouds, strong updrafts can carry ice particles upward repeatedly. As they rise and fall through regions of varying temperature, they collect additional layers of ice. This process can produce hail, which consists of concentric layers formed during repeated upward and downward motion. Even in ordinary rainstorms, however, the journey often begins in cold air. This reveals something subtle about rain. What feels soft and warm on the surface may have formed in air colder than most winter days at ground level. The rain that lands gently on a rooftop may have passed through multiple thermal zones before arriving. Temperature shapes precipitation long before it becomes visible. The vertical structure of the atmosphere is always shifting. As air masses move, warm and cold layers slide past one another. Storm systems organize these layers into patterns that determine the final form of what falls. The fall itself may feel simple, but its origin is complex. High above, ice crystals form quietly. They grow by collecting supercooled droplets. Gravity draws them downward. Warmer air melts them into rounded drops. Cooler air near the surface may reshape them once again. All of this unfolds without sound from the perspective of the ground. And once melting is complete, the drop continues its descent through the remaining stretch of air between cloud and soil. From that height to the surface, another set of forces takes over. Gravity accelerates the drop. Air pushes back. Wind may guide it sideways. The shape flattens slightly as speed increases. The ice has melted. The droplet is now fully liquid, rounded and smooth, and it begins the final stage of its fall toward the earth below. Once the ice has melted and the droplet is fully liquid again, the final stretch of its journey begins. Between cloud and ground lies a long column of air. Sometimes this distance is only a few thousand feet. In larger storm systems, it can be much farther. Within this space, gravity continues its steady pull, and the droplet begins to accelerate downward. At first, the drop gains speed. Gravity pulls every object toward the Earth at the same rate. But air resists movement. As the droplet falls faster, more air presses against its surface. The resistance increases with speed. Eventually, the upward force of air resistance becomes equal to the downward pull of gravity. At that point, acceleration stops. The droplet reaches what is called terminal velocity. For most raindrops, terminal velocity falls between about 14 and 22 miles per hour, depending on size. Smaller droplets fall more slowly because they have less mass and experience proportionally greater air resistance. Larger droplets fall faster because gravity has more mass to pull downward, though even they are limited by air pushing upward. This balance of forces shapes the drop as it descends. As it reaches terminal velocity, air presses more strongly against its underside. The bottom flattens slightly, while the top remains curved. The drop does not become pointed. It does not stretch into a tear. Instead, it becomes wider at the base and gently rounded above. If a droplet grows too large during its fall, the pressure from air resistance can cause it to distort further. The flattened underside may bow upward, forming a shape that is unstable. At a certain size, usually around 5 millimeters in diameter, the droplet breaks apart into smaller drops. These smaller droplets then continue falling at their own terminal velocities. This fragmentation prevents raindrops from growing endlessly large. Wind also plays a role during descent. Air currents moving horizontally can push falling droplets sideways. From the ground, rain may appear to slant at an angle rather than fall straight down. The stronger the wind, the greater the angle. Inside a storm, complex patterns of rising and descending air create swirling paths that droplets must travel through before reaching the surface. Even so, gravity always acts downward. The drop's path may curve slightly, but its motion is guided by the steady pull toward the earth. As droplets descend, they may continue to collide with other droplets, merging briefly before separating or joining permanently. The interior of a rain shaft is not empty. It is filled with countless falling drops, each moving at slightly different speeds. Larger drops overtake smaller ones. Some merge, some shatter. The pattern is dynamic, but governed by consistent physical laws. The surrounding air also influences evaporation during the fall. If the air below the cloud is relatively dry, some droplets may shrink before reaching the ground. Partial evaporation cools the air slightly and reduces the droplet size. In extreme cases, especially in very dry climates, droplets may evaporate completely before touching the surface. This phenomenon is known as virga. From a distance, rain appears to be falling from a cloud, but it vanishes before reaching the earth. Most rainfall, however, completes the descent. As the droplet approaches the ground, its shape stabilizes under steady terminal velocity. The final few feet pass quickly. A drop falling at 20 miles per hour covers the last 10 feet in less than half a second. Impact follows. But before that impact, there is a brief suspension in motion. A single rounded drop, shaped by gravity and air, moving through invisible currents, carrying water that has risen, cooled, frozen, melted, merged, and descended again. The fall is quiet, but purposeful. From ice crystal high above to liquid drop near the ground, the journey spans thousands of feet and multiple temperature layers. What reaches the surface has already undergone transformation. And when it meets soil, leaf, rooftop, or water, another set of changes begins. The descent ends in contact. The story of falling gives way to the story of arrival. The fall ends in contact. A rounded drop, shaped by gravity and air, meets the surface of the earth. The impact is brief, but what follows can last for years. When rain reaches soil, one of the first processes that begins is infiltration. Infiltration is the movement of water from the surface into the spaces between particles of soil. These spaces, called pores, vary in size depending on the type of soil. Sandy soil has larger pores, allowing water to pass through more quickly. Clay soil has much smaller pores, slowing the movement of water and sometimes causing it to pool at the surface. If the rain is gentle and the soil is dry, most of the water sinks downward. As droplets land, they spread outward slightly, then slip into the small openings between grains of sand, silt, or clay. Gravity pulls the water deeper. At the same time, another force acts alongside gravity. Capillary action. Capillary action is the movement of water through narrow spaces, due to the attraction between water molecules and the surfaces they touch. Water clings to soil particles. This adhesion, combined with the cohesion between water molecules themselves, allows water to move not only downward, but also sideways and even slightly upward within the soil. In very fine soils, capillary forces can draw water through small pores more slowly, but more steadily. The soil becomes a network of tiny channels, guiding water deeper into the ground. But not all rain infiltrates. If rainfall is intense, or if the soil is already saturated, water cannot enter quickly enough. The surface pores fill. Once they are full, additional water begins to move across the surface. This movement is called runoff. Runoff follows the shape of the land. It travels downhill, guided by slope and gravity. Across pavement, runoff moves quickly, forming shallow sheets that gather along edges and into drains. Across fields or forests, runoff moves more slowly, weaving around roots and stones, sometimes carving small temporary channels in loose soil. The balance between infiltration and runoff depends on several factors. Soil texture plays a major role. Sandy soil absorbs quickly but may not hold water for long. Clay soil absorbs slowly but retains moisture longer once saturated. Vegetation also matters. Plant roots create pathways in the soil, increasing its ability to absorb water. Leaves and ground cover slow the impact of falling drops, reducing erosion and giving water more time to sink in. Even the slope of the land affects the outcome. Steep surfaces encourage runoff. Flat surfaces encourage infiltration. As water moves downward through the soil, it eventually reaches deeper layers where the spaces between particles are completely filled with water. This zone is called the saturated zone. The top of this saturated region is known as the water table. Groundwater begins quietly here. Beneath the surface, beyond sight and sound, infiltrated rain joins vast reserves of underground water. It may move slowly through porous rock or remain stored for months, years, or even centuries. Some groundwater eventually emerges at springs. Some feeds rivers from below. Some remains stored deep underground until drawn upward by roots or human wells. This hidden movement is steady and slow. Meanwhile, at the surface, runoff continues its path. Small streams form where multiple trickles meet. Water gathers in shallow depressions. Puddles expand briefly before soaking in or evaporating. The ground reshapes slightly under repeated rainfall. Fine particles of soil may loosen and travel with the flowing water, carried downslope. Erosion begins subtly. A single rainfall may shift only a small amount of sediment. Over time, repeated rainfall can carve channels, deepen grooves, and gradually reshape landscapes. But even before rivers form, the meeting between rain and ground sets many processes in motion. Water cools the soil. Microorganisms awaken in moist conditions. Roots begin absorbing newly available moisture. From the perspective of the falling drop, contact is not an ending. It is a transition. Some of the water seeps downward into darkness, beginning a long underground journey. Some flows outward across the surface, joining other droplets in shallow paths. Some will evaporate again, rising invisibly back toward the sky, and some will gather. As runoff merges with runoff, small trickles combine. A thin stream begins to form, following the gentle slope of the land. The quiet descent from cloud to ground now becomes a horizontal movement across the earth. Rain that once fell as separate drops begins to move together, and the slow gathering of water continues towards something larger. Where runoff gathers, movement becomes more defined. What began as scattered droplets sliding across soil now begins to align. Thin threads of water, barely visible at first, follow the natural contours of the land. Gravity guides them. Each small depression becomes a pathway. Each shallow groove becomes a channel. A rivulet forms. Rivulets are narrow, temporary streams created by rainfall. They appear quickly during a storm and may disappear just as quickly once the rain ends. Yet even these brief flows carry weight. As they move downhill, they pick up loose particles of soil. Sand, silt, and organic matter are lifted and carried forward. Water is both gentle and persistent. As rivulets merge, they become small streams. The merging happens quietly. One path meets another. The flow deepens slightly. The current strengthens. What was once separate now moves as one. This gathering is organized by watersheds. A watershed is an area of land where all the rainfall drains toward a common outlet, such as a river, lake, or ocean. The boundaries of a watershed are defined by higher ground. Rain falling on one side of a ridge may travel toward one river system. Rain falling on the other side may travel somewhere entirely different. The shape of the land decides the destination. From above, watersheds resemble branching patterns, like the veins of a leaf or the roots of a tree. Small streams feed into larger ones. Those larger streams join even greater rivers. Each drop that joins the flow contributes to the motion of the whole. Gravity remains constant. Water moves from higher elevations to lower ones, always seeking the path of least resistance. Over time, repeated rainfall strengthens these paths. Channels deepen. Banks form. Sediment accumulates in some places and erodes in others. Sediment travels with the water. Fine particles remain suspended in the current, giving some rivers a cloudy appearance after heavy rain. Larger stones roll along the riverbed, pushed slowly by the force of moving water. This transport of sediment shapes landscapes over long periods. Rivers carve valleys not in a single storm, but through countless small events repeated across centuries. Rainfall is the beginning of that carving. When rain feeds a stream, it increases the volume of water moving through the channel. The greater the volume, the greater the force exerted against the riverbanks and bed. Over time, this force smooths stones, shifts sandbars, and alters the course of the river itself. Even gentle rain contributes to this process. In forested areas, roots help hold soil in place, slowing erosion. In open fields, runoff may move more freely. In urban spaces, paved surfaces accelerate runoff, sending water quickly into drainage systems and then into rivers downstream. Every surface influences how quickly rain reaches a stream. As streams merge and grow, they form rivers capable of traveling long distances. Some rivers flow only a few miles before reaching a lake or sea. Others stretch across entire continents, carrying water from mountain ranges to distant coasts. And throughout their journey, rivers continue to receive rainfall. Storm after storm adds new water. Tributaries join the main channel. Seasonal rains increase flow. drier periods reduce it. The river rises and falls in response to rainfall patterns across its watershed. From the perspective of a single drop, the journey is long and varied. It may move from cloud to soil, from soil to rivulet, from rivulet to stream, from stream to river. It may travel for days, months, or longer before reaching a larger body of water. Along the way, it shapes and is shaped. It carries minerals. It cools banks. It reflects light. It supports fish and plants that depend on steady flow. Its movement is guided entirely by gravity and terrain. Rainfall does not end at the ground. It reorganizes itself into pathways that reshape the land quietly over time. And as rivers continue their slow movement toward lakes and seas, some of the water they carry nourishes the roots of plants along their banks. Rain that once fell freely now supports life in another form. From gathering streams to flowing rivers, the next quiet shift in this journey turns toward the living systems that depend on this steady supply of water. As rivers move steadily across the land, some of their water never reaches the sea. Before runoff becomes stream, before stream becomes river, part of the rain pauses among roots and leaves. Rain meeting plant life is not sudden. It is quiet nourishment. When water infiltrates soil, it fills the tiny spaces between soil particles. Within those spaces are also roots, thin and branching, reaching outward in search of moisture. The smallest roots are covered in microscopic extensions called root hairs. These fine structures increase surface area, allowing plants to absorb more water from the surrounding soil. Water moves from the soil into the root through a process driven partly by osmosis. Osmosis occurs when water moves across a semi-permeable membrane from an area of higher concentration to lower concentration. Inside root cells, dissolved minerals create a gradient that draws water inward. Once inside the root, the water enters a network of transport tubes called xylem. Xylem vessels run upward through the plant, forming continuous channels from roots to leaves. The movement of water through xylem is powered largely by a process called transpiration. As water evaporates from tiny openings in leaves, called stomata, it creates a gentle pulling force that draws more water upward from below. In this way, rain that entered the soil can travel upward against gravity. The movement is slow but steady. A tall tree can lift water dozens of meters from its roots to its highest leaves, using this combination of cohesion between water molecules and evaporation from leaf surfaces. Rain supports this upward flow by replenishing soil moisture. Without rainfall, soil dries. As soil moisture decreases, plants close their stomata to reduce water loss. This also reduces the intake of carbon dioxide needed for photosynthesis. With sufficient rain, stomata open again. Gas exchange resumes. Photosynthesis continues. Water is central to this process. During photosynthesis, plants use sunlight to convert carbon dioxide and water into glucose and oxygen. The water absorbed from rain becomes part of the plant's internal chemistry. Some of it is incorporated into sugars. Some is released again into the air through transpiration. Rain also washes leaves. Dust, pollen, and pollutants that accumulate on leaf surfaces are carried away by falling droplets. Clean leaf surfaces allow more efficient light absorption. Water beads briefly on the waxy coating of leaves before sliding downward to the soil below. In forests, rainfall is partially intercepted by the canopy. Some water evaporates directly from leaf surfaces before ever reaching the ground. Some drips from leaf to leaf, slowing its descent. This interception reduces erosion by softening the impact of raindrops on soil. Plants do not simply receive rain, they shape how it moves. Roots stabilize soil, reducing runoff. Leaves break falling drops into smaller ones. Vegetation slows the movement of water across the ground, allowing more infiltration. In this way, plant life moderates the flow between sky and soil. Even grasses and small shrubs participate. After rainfall, fields often appear more vibrant. Leaves stand upright. Colors deepen. This visual change reflects renewed turgor pressure within plant cells. When cells are filled with water, they press outward against their walls, giving leaves structure and firmness. Water provides not only nourishment, but form. Some of the rain absorbed by plants will remain within tissues for days or weeks. Some will move upward and evaporate again into the atmosphere. In fact, a significant portion of atmospheric moisture originates not only from oceans, but from transpiration by plants. Forests, especially tropical rainforests, release vast amounts of water vapor back into the air. This recycled moisture can contribute to future rainfall. So rain that falls into a forest may rise again within hours. The exchange continues. Rain feeds plants. Plants release vapor. Vapor condenses. Rain falls again. As streams move outward and rivers continue their course, plants along their banks absorb part of the flow. Some water remains stored in trunks and stems. Some evaporates into the sky, and some continues its journey toward larger bodies of water. Beyond forests and fields, beyond river valleys and wetlands, most of Earth's water resides in a vast and continuous expanse. The oceans hold the majority. Rain that nourishes land often began over open water. And as rivers carry fresh water back toward the sea, the cycle widens once more. Beyond forests and fields, beyond rivers and lakes, lies the largest reservoir of water on Earth. The oceans hold about 97% of all the planet's water. They stretch across more than 2/3 of the surface, forming a continuous body that connects every continent. Most of the rain that falls on land began here. Evaporation occurs most intensely over the ocean. When sunlight reaches the surface of seawater, it warms the upper layers. Water molecules at the surface gain energy. Some move fast enough to escape into the air as vapor. During this transition from liquid to gas, salt and other dissolved minerals are left behind. Only pure water molecules rise. This is why rainwater is fresh, even though it began over salt water. The ocean steadily loses water to the atmosphere through evaporation, but it also gains water from rivers and rainfall. The balance between evaporation and precipitation varies by region. In some parts of the ocean, evaporation exceeds rainfall. In others, rainfall dominates. Once water vapor rises into the atmosphere, wind begins to move it. Moisture does not remain fixed above the location where it evaporated. Large-scale wind patterns carry water vapor across vast distances. Air currents can transport moisture thousands of kilometers before it condenses and falls as rain. In some cases, this transport becomes highly organized. Meteorologists use the term atmospheric river to describe long, narrow bands of concentrated moisture moving through the atmosphere. These invisible rivers in the sky can stretch for hundreds or even thousands of miles. When they reach land and encounter mountain ranges, the air is forced upward, cools, and releases its moisture as heavy rainfall. In this way, ocean water is redistributed inland. Regions far from the coast often depend on moisture that originated over distant seas. Rain falling on mountains may have evaporated from tropical waters days earlier. Snowpack that accumulates during winter may have begun as vapor above warm ocean currents. The movement is continuous. Evaporation lifts water from the ocean. Winds carry it across continents. Condensation forms clouds. Rain falls onto soil and rivers. Rivers return water to the sea. The ocean is both origin and destination. Yet the journey between those points may take many forms. Some vapor condenses quickly and falls back over the sea. Some travels inland and becomes groundwater. Some nourishes crops. Some freezes into mountain snow and remains stored for months before melting. Rain over land often represents a transfer. Water that evaporated from the ocean becomes fresh water inland. It replenishes lakes. It fills reservoirs. It supports ecosystems that depend on rainfall. And when rivers carry that fresh water back toward the sea, they bring with them minerals dissolved from rock and soil. Over long timescales, this process contributes to the salt content of the ocean itself. Minerals carried by rivers accumulate in seawater because evaporation removes only pure water, leaving dissolved salts behind. The ocean slowly grows saltier through this steady exchange. At the same time, marine organisms incorporate minerals into shells and skeletons, helping balance the system. Even here, cycles operate quietly. From above, the ocean appears calm in some regions, restless in others. Yet beneath the surface, energy from the sun and rotation of the earth drives currents that circulate water globally. Warm surface water moves toward colder regions. Cold water sinks and travels along the deep ocean floor before rising again elsewhere. This global circulation influences evaporation patterns. Warmer waters evaporate more readily, feeding moisture into the atmosphere. Cooler waters evaporate more slowly. These differences help shape rainfall patterns across the planet. Rain that falls tonight may have risen from tropical seas weeks earlier. It may have traveled across continents as vapor, condensed into clouds above distant mountains, and descended onto forests, fields, or cities. The cycle does not pause. The ocean releases. The atmosphere carries. The land receives. Rivers return. And beyond the scale of oceans and continents, there is an even wider rhythm at work. The movement of water across the globe is part of a larger planetary pattern. Evaporation, condensation, precipitation, and return form a system that has operated for billions of years. To understand rain fully, attention widens once more. From ocean basins to mountain peaks, from rivers to groundwater, all of it belongs to a single continuous process. A planetary rhythm that moves water endlessly through sky, land, and sea. From oceans to clouds, from clouds to rivers, the movement of rain is part of something larger than any single storm. It belongs to the global water cycle. This cycle is not a straight line. It is a continuous loop, a planetary rhythm that has been operating for billions of years. Every drop that falls is part of this circulation, moving between ocean, air, land, and life. Nearly 97% of Earth's water is saltwater, held in the oceans. The remaining 3% is freshwater. Of that small fraction, most is locked away in glaciers and ice caps. Only a tiny portion exists as liquid freshwater in rivers, lakes, soil, and groundwater that is easily accessible. And yet, this small portion is constantly renewed. Evaporation lifts water from oceans, lakes, and soil. Transpiration releases vapor from plant leaves. Together, these processes are sometimes called evapotranspiration. Water rises invisibly into the air, molecule by molecule, carried by heat from the sun. As the vapor rises, it cools. Cooling leads to condensation. Tiny droplets form around microscopic particles in the atmosphere. Clouds gather. Billions of droplets remain suspended until gravity takes hold. Rain falls. Snow falls. The cycle continues. What makes this cycle remarkable is its continuity. Water molecules do not disappear. They change state. They move location. They shift between liquid, vapor, and ice. But the molecules themselves remain the same. A single molecule of water composed of 2 hydrogen atoms and 1 oxygen atom may spend time in the ocean, then rise into the air, fall onto land, flow through a river, freeze into ice, melt again, seep into soil, enter a plant, evaporate once more, and return to the sea. There is no final destination. On average, a water molecule spends about 9 days in the atmosphere before falling as precipitation. It may remain in a river for weeks. It may reside in a lake for years. It may stay locked in groundwater for centuries. In glaciers, water can remain frozen for thousands of years. The timing varies, but the movement continues. The energy driving this cycle comes primarily from the sun. Solar radiation warms the surface of the Earth, especially the oceans. This warmth powers evaporation. Without the sun's energy, the cycle would slow dramatically. Gravity also plays a central role. Gravity pulls water downward as rain. It guides runoff downhill into rivers. It shapes the flow of streams toward the sea. The water cycle depends on both solar energy and gravitational pull working together. On a global scale, the balance between evaporation and precipitation is remarkably stable. The amount of water evaporating from oceans roughly equals the amount returning through rainfall and river flow. Over long periods, this balance maintains the total volume of water on Earth. Even during climate shifts, the total quantity of water remains nearly constant. What changes is distribution. Some regions receive more rainfall. Others become drier. Ice expands or melts. Sea levels rise or fall slightly, yet the molecules continue cycling through the same pathways. The water falling tonight may represent only a brief pause in this vast system. It may have risen from the ocean weeks ago. It may flow back there within days, or it may linger underground for years before returning. The scale of the cycle stretches beyond human lifetimes. Civilizations have risen and fallen while water continued its steady circulation. Rivers have shifted course. Ice ages have come and gone. Through it all, the same cycle persisted. When rain taps softly against a window, It is part of a planetary exchange far older than memory. The drop landing on your hand is participating in a rhythm that includes oceans, clouds, glaciers, rivers, soil, and living cells. And this rhythm extends not only across space, but across time. Water molecules themselves are ancient. Long before humanity existed, before forests covered continents, before mammals walked the land, water was already cycling between sky and sea. To understand rain fully, the perspective widens again. Beyond continents and oceans lies deep time. The same molecules moving through the cycle today may have moved through very different worlds long ago. Beyond oceans and continents, beyond rivers and forests, the story of rain stretches into deep time. Water itself is older than humanity, much older than cities, languages, or even the species that now watches the sky for clouds. The molecules that form a single drop of rain are composed of hydrogen and oxygen atoms that have existed for billions of years. Hydrogen formed shortly after the universe began. Oxygen formed later inside ancient stars and was released when those stars ended their lives. Long before Earth had oceans, the atoms that make up water already existed. As the early Earth cooled more than 4 billion years ago, water vapor condensed into liquid. Rain fell onto hot rock. Oceans gathered. The cycle began. Since then, the same water molecules have moved through countless forms. The rain falling tonight may contain molecules that once drifted in ancient seas, where early life first developed. Some may have flowed through rivers that cut across landscapes now buried beneath layers of sediment. Some may have been locked inside glaciers during ice ages, frozen for tens of thousands of years before melting and returning to circulation. Dinosaurs drank rain. The same type of water molecule that touches your skin today may once have passed through the body of a massive reptile walking across prehistoric plains. It may have flowed through the veins of creatures long extinct. After leaving those bodies through evaporation or decay, it returned to the air, condensed, and fell again. Water does not remember, but it persists. Glaciers store water for long periods. In polar ice sheets, some water has remained frozen for hundreds of thousands of years. When those glaciers melt, ancient water re-enters the rivers and oceans. It mixes with newly evaporated moisture. The distinction between old and new disappears. Groundwater can also hold water for centuries. Rain that infiltrates deeply into underground aquifers may remain stored there for generations. Slowly moving through porous rock, it may take decades or longer to emerge again at the surface. During that time, it is shielded from sunlight and air, resting in quiet darkness. When it eventually rises through a spring or is drawn up by a well, it rejoins the active cycle. Tonight's rain may have taken many paths before arriving. Some molecules may have evaporated from the ocean only days ago. Others may have traveled through plant leaves in a rainforest thousands of miles away. Some may have been frozen into mountain snow last winter and melted only recently. All are part of the same ongoing exchange. What makes this continuity remarkable is not only the age of the molecules, but their repetition. Water cycles endlessly. It does not wear out. It does not decay into something else under normal Earth conditions. It shifts state. It changes location. It remains water. The rain falling now may once have touched a medieval battlefield, soaking the cloak of a night beneath a grey sky. It may have fallen along the banks of the Nile in ancient Egypt, landing near the sandals of a pharaoh. It may have condensed above forests where dinosaurs once moved through heavy air. The atoms within it have been present through each era. Yet the drop itself feels immediate. It lands softly. It cools the air. It soaks into soil. It feeds a root. It flows into a river. It evaporates again. Deep time narrows into the present moment. When rain falls outside your window, it carries no visible sign of its age. It appears new, fresh, temporary, and in a sense, it is new because its arrangement in that particular droplet has never existed before. But its components are ancient. They have circled the planet countless times. They have passed through oceans, clouds, ice, stone, leaf, and lung. Tonight's rain may feel ordinary, yet it is part of a story that began billions of years ago and will continue long after this moment passes. And as it falls now, gently and steadily, it returns once more to the present. The ancient becomes immediate. The planetary becomes personal. A single drop lands, and the cycle continues. As daylight fades, the atmosphere changes again. Rain at night feels different from rain during the day, even if the amount falling is exactly the same. The difference begins with temperature. After sunset, the ground cools. During the day, sunlight warms the surface of the earth. Pavement, soil, rooftops, and vegetation absorb heat. When the sun sets, that energy radiates back into the air. The surface gradually cools, and the air just above it cools as well. Cooler air near the ground is denser and more stable, meaning it resists rising. This stability can soften wind near the surface. With less upward mixing of warm air, nighttime rain often falls through calmer layers close to the ground. The drops descend into cooler, steadier air. The result can feel gentler, more uniform. Sound changes too. At night, background noise typically decreases. Traffic slows. Human activity quiets. The absence of competing sounds makes rain more noticeable. A steady fall that might blend into daytime noise becomes distinct in darkness. Reduced visual input heightens hearing. In lower light, the visual system provides less information. Edges blur, color fades. The brain naturally shifts more attention towards sound. When the eyes have fewer details to process, the ears become more alert to subtle patterns. Rain provides one of those patterns. Each drop striking roof, leaf, or pavement creates a small vibration. At night, these vibrations stand out more clearly. The rhythm feels fuller, more immersive. Without bright light and moving shapes to divide attention, the sound occupies a larger portion of perception. Darkness softens edges. Cloud cover at night reduces reflected light from the moon and stars. Streetlights glow faintly through mist. Reflections shimmer across wet surfaces. The world appears simplified. Shapes lose sharp contrast. Motion slows. In this softened visual environment, rain becomes a primary sensory event. The air itself often feels cooler and denser. Cooler air carries sound differently. Under certain conditions, nighttime air can allow sound to travel farther. The steady fall of rain may seem to wrap more fully around a space. Indoors, the effect deepens. With lights dimmed and activity paused, The rhythmic pattern of rainfall can fill the quiet of a room. The predictable repetition reduces the sense of unpredictability. Instead of isolated sounds standing out sharply, the rain creates a continuous background. Even the smell may feel stronger at night. Cooler air holds less water vapor before reaching saturation, so scents can linger closer to the ground. The earthy fragrance of wet soil may feel more concentrated. Without sunlight dispersing warmth upward, moisture remains near the surface longer. Rain at night narrows attention. There are fewer visual cues to interpret, fewer distractions. The sound becomes steady and central. The temperature cools slightly. Air feels heavier but calmer. In evolutionary terms, nighttime once carried uncertainty. Darkness limited sight. Predictable environmental cues helped reduce vigilance. A steady, continuous sound like rain signals stability rather than sudden threat. The pattern does not spike. It does not change abruptly. It continues. As rain falls through night air, the world seems enclosed within its sound. Edges blur, reflections stretch across pavement, leaves glisten under faint light. The cycle continues unseen above, but at ground level, the experience is intimate. Cooler ground stabilizes air. Reduced light heightens hearing. Darkness softens detail. Rain becomes more noticeable. And then, sometimes, it stops. The steady sound fades gradually. The last few drops fall farther apart. The rhythm loosens. In the quiet that follows, attention shifts from presence to absence. What happens when rain does not return for a while? What changes when the sky remains dry? The cycle pauses, but it does not end. The ground waits. The air shifts. Moisture lingers or fades. And in that quiet dryness, another chapter begins. After the steady rhythm of rain fades, the air feels different. The absence is subtle at first. The ground begins to dry. Puddles shrink. Leaves lose their gloss. What was once a continuous sound becomes stillness. When rain pauses for days or weeks, the balance between evaporation and precipitation begins to shift. Under sunlight, water at the surface continues to evaporate. Moisture rises invisibly from soil, pavement, rivers, and leaves. If new rain does not replace it, the amount of water stored in the soil decreases gradually. This reduction is called soil moisture loss. Soil moisture is more than surface dampness. Water fills tiny pores between particles. It clings to mineral surfaces. It supports microorganisms and plant roots. When evaporation exceeds precipitation over time, those pores empty. The ground becomes firmer. Fine particles loosen more easily. Plants respond quietly to this change. As soil dries, roots encounter less available water. Inside the leaves, tiny openings called stomata begin to close. Stomata regulate gas exchange. When open, they allow carbon dioxide to enter for photosynthesis. They also allow water vapor to exit through transpiration. When water is scarce, stomata close to conserve moisture. This reduces water loss but also slows photosynthesis. Growth may slow. Leaves may droop slightly as internal pressure decreases. The change is gradual, not immediate, but steady. Above, cloud formation becomes less frequent when the atmosphere holds less moisture. If evaporation continues but atmospheric conditions do not favor condensation, clouds may thin. Clear skies allow more sunlight to reach the surface, increasing surface temperatures. Warmer ground can accelerate evaporation further, deepening dryness. The cycle tilts. In regions experiencing prolonged dryness, this imbalance becomes more pronounced. Evaporation consistently exceeds rainfall. Streams shrink. Rivers recede toward their banks. Reservoir levels fall slowly. Groundwater is drawn down faster than it is replenished. Yet the shift is rarely abrupt. Drought develops gradually. It is defined by duration and pattern rather than a single event. Weeks without rain can reduce soil moisture. Months can affect rivers and lakes. Years can alter ecosystems. The land responds in stages. Dry soil absorbs less water when rain finally does return, at least at first. Hardened surfaces may increase runoff rather than infiltration. Plants adapted to periodic dryness may endure by conserving water. Others may shed leaves or enter dormancy. Clouds themselves form less easily when atmospheric moisture is low. Condensation requires sufficient water vapor and cooling. Without adequate moisture in the air, rising currents produce thinner clouds. Even if clouds form, they may not contain enough droplets to generate rainfall. The atmosphere reflects the conditions below. Dry soil reduces evaporation. Reduced evaporation lowers atmospheric humidity. Lower humidity makes cloud formation less likely. The feedback loop reinforces dryness. Yet the cycle does not stop permanently. Oceans continue to evaporate. Winds continue to transport moisture. Eventually, atmospheric patterns shift. Cooler air masses move in. Moisture accumulates once more. Even in drought, the larger water cycle persists. Deep underground, groundwater may still move slowly through rock. In shaded valleys, moisture lingers longer. In distant regions, rainfall may be abundant while one area remains dry. The balance shifts unevenly across the planet. For those on the ground, the absence of rain feels quiet but tangible. The air may seem lighter, less humid. The scent of soil fades. Nighttime no longer carries the steady rhythm against rooftops. Yet dryness carries its own stillness. Without falling drops, surfaces remain unchanged. Dust gathers, leaves rustle instead of glisten. Streams narrow into defined channels. And then, often without dramatic announcement, clouds begin to gather again. Moisture transported from distant seas accumulates. Air cools. Condensation begins. Droplets form around tiny particles once more. The pause ends. Rain returns not as interruption, but as restoration. After a period of imbalance, the cycle leans back toward replenishment. Soil pours open again to receive water. Rivers begin to rise. Leaves respond. Dryness gives way to renewal. The shift back toward balance is gradual, steady, and familiar. The sky darkens. The air cools slightly. And once again, rounded drops begin to fall. Clouds gather again, almost quietly. After a stretch of dryness, the first return of rain can feel like a small adjustment in the air. The scent shifts. The light softens. The ground prepares. When rain returns, balance begins to restore itself. The first changes happen at the surface. Dry soil, which had tightened and hardened under sun and wind, begins to loosen as water seeps back into its pores. Infiltration resumes. Capillary channels fill. The upper layers of earth regain moisture that had slowly evaporated away. With sufficient rainfall, soil moisture rises back toward its usual level. Plants respond quickly to this change. Roots absorb newly available water. Inside leaves, stomata reopen more fully. Transpiration increases. Photosynthesis strengthens. Cells regain internal pressure and leaves lift slightly as water fills their tissues again. The deepened green of foliage after rain reflects this restored hydration. Rain restores not only water, but function. Streams that had narrowed begin to widen. Small tributaries that had gone quiet may resume flowing. Rivers receive additional volume from runoff and groundwater recharge. Even a modest rainfall can alter water levels over time if it continues steadily. Reservoirs refill slowly. Groundwater, though slower to respond, begins to rise again as infiltrated water moves downward. Aquifers that had been drawn down begin their gradual replenishment. The process is not immediate, but the direction shifts. Temperature moderates as well. Rain cools the surface by absorbing heat during evaporation and by replacing dry, heated air with cooler downdrafts. Wet soil reflects and absorbs sunlight differently than dry soil. With moisture restored, the extremes of temperature soften slightly. Humidity increases. The air feels fuller, but also more stable. Evaporation from wet surfaces adds moisture to the lower atmosphere, preparing conditions for future cloud formation. The feedback loop that once reinforced dryness now begins reinforcing moisture. Rain also clears the air. As droplets fall, they capture small airborne particles and carry them to the ground. Dust, pollen, and other fine materials are removed through wet deposition. The result is air that can feel cleaner and less sharp to breathe. Visibility may improve after rain passes. Even ecosystems beyond the visible respond. Microorganisms in soil reactivate with moisture. Seeds that remain dormant during dry conditions may begin to germinate. Insects emerge. Birds adjust their patterns to renewed water availability. Balance is not dramatic. It is a quiet realignment of moisture, temperature, and flow. The cycle tilts back toward replenishment. Rivers resume their steady movement. Leaves glisten. The scent of soil returns. Rainfall does not solve imbalance in a single moment. It restores gradually, layer by layer. Soil moisture increases. Surface runoff decreases as infiltration improves. Groundwater rises. Air cools slightly. Particulates settle. The landscape stabilizes. Over time, repeated rainfall events rebuild what dryness reduced. And through this restoration, something familiar returns to human experience. Predictability. The pattern of rain returning after dryness reinforces the sense that cycles continue, that pauses are temporary, that imbalance shifts back toward equilibrium. The steady sound against rooftops becomes reassurance rather than interruption. Rain returns, not urgently, not dramatically, but steadily. And as balance restores itself in soil, river, and air, attention can turn inward. The cycle is physical, measurable, and planetary. Yet it also intersects with memory, with how humans have long experienced seasonal patterns, with how repetition lowers vigilance and fosters calm. The restoration of balance in the landscape mirrors something quieter in perception. Rain falls again, the air softens, and the experience becomes not only environmental but personal. Rain returns to the landscape, and something familiar stirs in human memory. Long before cities, before artificial light and insulated walls, humans lived closely tied to seasonal patterns. Rain meant water for drinking, for plants, for animals. It meant relief after heat. It meant the possibility of growth. Over time, these repeated experiences shaped expectation. Humans evolved in environments where rainfall followed cycles. Wet seasons alternated with dry ones. Storms arrived and passed. Rivers rose and receded. The regularity of these patterns helped establish a sense of predictability. Predictability lowers vigilance. The nervous system constantly scans for change. Sudden shifts in sound or light can signal danger. But when patterns repeat in steady, recognizable ways, the body relaxes. Rain often arrives as a continuous sound, not a sharp interruption. Its rhythm does not spike unpredictably. It sustains. This steadiness matters. A steady rainfall creates a uniform acoustic field. Instead of isolated noises puncturing silence, there is a constant layer of sound. Environmental contrast decreases. With less contrast, the nervous system perceives fewer abrupt events to monitor. Rain reduces environmental sharpness. Light dims under cloud cover. Colors soften. Reflections shimmer rather than glare. Movement slows as people seek shelter. The overall pace of activity changes subtly. These sensory shifts combine. Lower light, steady sound, cooler air, increased humidity. Together, they create a sensory environment that feels enclosed and consistent. The brain interprets consistency as safety. Human memory is associative. The sound of rain may connect to early experiences. Resting indoors while weather moved outside, listening to drops against a window, watching puddles form along a street. Even without conscious thought, repeated exposures shape emotional tone. Rain often coincides with stillness. Outdoor tasks pause. Travel slows. Conversations quiet. The body tends to settle when the environment settles. Over years of experience, rain becomes linked with slowing down. This association can persist even in modern environments where daily routines are less dependent on weather. When rain falls at night, the dimming light and steady sound combine with reduced activity. Fewer visual cues compete for attention. Hearing becomes more prominent. The soundscape becomes predictable and continuous. Repetition lowers vigilance. A repetitive, non-threatening stimulus allows attention to drift. The mind no longer needs to track sudden changes. Instead, it rests within the pattern. There is also an evolutionary element to water itself. Access to fresh water was once directly tied to survival. Rain meant replenishment of streams and pools. It signaled that resources would continue. The return of rain after dryness restored balance not only in the landscape, but in human expectation. Even today, a steady rainfall can evoke a subtle sense of reassurance. The cycle continues. Clouds gather, rain falls, rivers flow, soil absorbs. Evaporation lifts moisture again. The repetition extends beyond individual memory into generational experience. Rain becomes familiar not because it is identical each time, but because its structure remains consistent. The rounded drop, the steady fall, the softened light, the rhythmic sound. Across lifetimes, these elements repeat, and repetition builds familiarity. Familiarity builds calm. When rain falls now, it may feel less like an isolated weather event and more like participation in something ongoing. A pattern that has repeated across centuries. A cycle that does not hurry. The body recognizes steadiness. The mind recognizes pattern. The sound continues without urgency. And within that continuity, attention can soften further. Rain does not demand action. It simply falls. Water rises, cools, condenses, falls again. Somewhere, at this moment, rain is touching ground. The cycle is already continuing quietly, whether you notice it or not. And in that quiet continuation, rest becomes possible.